Great. Welcome. This is the last session of the day, and we have some really exciting things to share with you. So my name is Dmitry, and I run business development for all advertising and marketing customers of Amazon Web Services. So today's session is a lot about machine learning and some really interesting know-how that the customer would like to share with you. So machine learning is super important, lots of great announcements at reInvent. And this is just an example of how machine learning can make a big business difference for this specific use case. So without further ado, I would love to introduce Team Smarto here on stage. Please give them a warm welcome.
Thank you, Dimitri. Hello, good afternoon, everybody. So my name is François Guéraz. I'm a systems architect at Smarto. And it's my pleasure today to introduce this talk by Janko Kovacevic, our machine learning engineer. Smarto is an in-app monetization platform. We connect advertisers with app publishers around the world to create the perfect ad campaigns and help publishers generate revenue. To begin, I will introduce you to the concept of in-app monetization and how the integration of our SDK facilitates the connection to our platform. I will talk about the main problem that we see with this current approach and how we at Smarto use machine learning to tackle that particular issue. So in order to explain how in-app monetization works, I'm going to walk you through a little story. And so you take an awesome developer, and sure enough, you end up with an amazing app. You publish it on the App Store of your choice, and it becomes an instant hit. You start getting users, and your user base grows. And obviously, you want to monetize this application and tap into this potential. One sure way of doing this is to partner with Smarto and integrate our SDK. Once that's done, we can start monetizing your app and send money your way. So, now for the example of how that works in real life. Once you've republished your application with our SDK, we can start displaying ads. In order to do that, we need some information that are going to be sent to us through our SDK. As an app publisher, you have a lot of information about your users. In this example, we have gender, age, country, and device type. And we have many more, and Janko will come back to that later. You send us this information, and as well as the application, at space ID, and all that sort of things. And the SDK will make a request to our co-auction platform. The co-auction platform will then match your ad request to a list of demand partners. So demand partners are the companies that are in contact with the advertisers, the marketers. They are the companies that the marketers use to target segments of the population. They know which particular type of user to target for which ad. So we have a list of them for every ad request, and we send the ad request in an auction-style kind of action. We send the ad request as bid request to the demand partners, and hopefully some of them will reply with some interest and will bid on the ad. In this case, which is a very optimistic one, the demand partner 101 will win the auction with the $12 bid. This is a very simplified example. There's many other rules in place, but this would be the example. And also it's extremely optimistic because in the vast majority of cases, there is actually no interest in the ad space. So an auction typically looks more like that, with everybody responding no ads and the auction having no winner. This creates many issues for us and for our partners. So for the publishers, it's a waste of time that they spend waiting for us to reply with no ads while we conduct the auction. And for us, it's a waste of money that's mostly spent as a waste of compute and wasted CPU and the waste of bandwidth sending the bid request to the demand partners. So in order to tackle this problem, 2 years ago, we started investing in a traffic filtering service. Its job is to receive the ad requests before we rerun the auction. And it makes a prediction based on previous behavior as to if the demand partners are going to be interested at all or not in the ad request. So if it predicts that there will be no interest, in that case, we just stop the auction right there and reply no ad to the publisher. We save money not running the auction, and the publisher has an immediate response that we don't have an ad to serve for them. On the other hand, if we think that there might be an interest on the side of the demand partners, then we run the auction as usual. In order to do this, we've put this architecture in place. So this is a simplified data flow view of the architecture. Our core auction platform is our historical product, and we start from there. That's the piece that receives the auction from the publishers. So for every ad request that we receive, we generate many, many events. They correspond to the decision making and to the response of the demand partners. And they are completely out of order. We send them to the data pipeline as soon as we receive them. So they are very hard to make any sense of because of the volume and the fact that they are out of order. So the main job of the data pipeline is to aggregate the data into sessions, which we call sessionization. Once that's done, we have a data lake. It's a sessions data set in this example. And then this data is consumed by our model building service that runs periodically to produce models that are stored on a repository. And then the traffic filtering service periodically loads them to serve live traffic. This is a brief overview of all the AWS products we use in order to achieve this. So on the compute side, for our core auction platform, we use EC2. And then the data is streamed to Amazon Kinesis on the top right corner. It's streamed to the data pipeline using Kinesis and processed with EMR. Then all of our data is stored into S3. And machine learning itself uses EMR again for reasons that Janko will explain later. And once that pre-processing is done, we use SageMaker to do the actual training. The models again end up on S3, and the traffic filtering service runs on ECS. So that worked very well, and we achieved many goals with that, and we had great cost reductions already. But we tasked Janko and his team to improve the system in 3 main areas. First, we wanted to improve traffic filtering itself. So improving it means making it more accurate and all the metrics that Janko will talk about later. We wanted to reuse the existing infrastructure because we had invested a lot in terms of business logic in it already, so we didn't want to reinvent everything. And finally, we wanted to have a real ML development framework that we could use to apply best software development practices to machine learning projects. So it's now time for Janko to take place on stage and tell you in details how they have achieved this goal. Thank you very much.
Thank you. So thank you, Francois. This was a really nice introduction. Good afternoon, everybody. My name is Janko Kovacevic. I am a machine learning engineer at Smato. I have written my first line of code at the age of 15. This was 12 years ago, and I have been a professional software developer for the last 4 years. I have completed my education 2 years ago. I have obtained a master's degree at computer science, and for the last 2 years, I have been working as a machine learning engineer. When we started our first machine learning project at Smato, we realized the ecosystem is not mature. When you start a project, you need to answer to a couple of questions. First of all, what kind of machine learning are you doing? Is it supervised or maybe reinforcement learning? And what about your data? Can you fit it on a single machine or you need to process it in distributed environment? The answers to these questions will tell you which tools you need to use. And within this talk, I want to tell you how we at Smato approach supervised machine learning problems, and I also want to tell you how we tackled the traffic filtering problem, which Francois explained at the introduction. So one moment, I have some technical issues with my, let's see. Can I please get some help from the, it doesn't want to switch my slide. Let me, okay, there we go. Okay, so, but before I can state explicitly what is the purpose of our model, I need to tell you that we had a rule-based model in our production environment. And this rule-based model was used to filter the traffic, but there was one issue. No matter how many new explicit business rules we added to the model, we couldn't improve its performance. We couldn't truly capture the true essence of why are demand partners bidding. And there was another problem with this approach. The problem was that if we kept on adding more and more business rules, the maintenance complexity of the model increased. And since we have terabytes of data at our disposal, why not let machine learning model learn the bidding patterns from the data? So to put explicitly, the purpose of the model is to predict whether or not demand partners will be interested in auction. It needs to tell our core auction platform, hey, based on the incoming request details, you need to either start an auction or stop an auction. And I want to give you a slightly better picture of what data we have at our disposal when the auction starts. Since Mato is an ad exchange, we operate according to some protocols. And there is this one protocol called Open RTB. The full name is Open Real-Time Bidding. And within this protocol, it is defined which data can be exchanged between publishers, SMATO, and demand partners. So here is one example of OpenRTB. So when an auction starts, I know, of course, the time of an auction. I know where the request is coming from. I know which city it is, which country it is. I know what is the application, and I know the resolution of an ad space. Besides this information, I know much more. And some combination of features are more interesting than the others. Imagine what happens if you combine the country code and the request time. Imagine it's 8 p.m., United States, people are coming from work, they're commuting, they're on their mobile phones. And if I observe my auctions between 8 p.m. and 11 p.m., I can see my auctions are getting filled in the United States. But if I do the same in 3 a.m., I can see demand partners are not bidding. The interest of demand partners has shifted to other regions in the world. So besides the features listed here, we have 70 more features according to OpenRTB protocol. For instance, the connection type. I know if an ad request is coming from a 2G network, 3G network, maybe 5G or Wi-Fi. And this is also a relevant predictor because imagine if you're a demand partner and you're offering a video ad, you will most likely not send it through a 2G network because the video would buffer for a long time. So now I want to explain to you how did we create model building service. So I need to get back to this diagram. And let's do a slight recap. So the purpose of the model building service is to take a chunk of our session data set, it needs to process it, it needs to use it to build machine learning model, and after the model had been built, it will place the model back on S3. From S3, the traffic filtering service will pick it up, load it into the memory, and it will use it to answer the queries from core auction platform. So how did we create the model building service? Whenever we start machine learning project at SMATO, we started by designing machine learning pipeline. And machine learning pipeline is a piece of software to whom you can provide a data set, and you can run the whole data set. It will reformat the data set, and it will use it to build machine learning model. So the output of machine learning pipeline is the machine learning model. And here is how our machine learning pipeline looks like. So this is pretty big diagram, but bear with me. Let me walk you through it. So let's start from the furthest left side. We start with our session data set. So session data set is a collection of our historical auctions. Every single row within my data set represents one auction which occurred into the past. And I know for every single auction, I know where it happened, when it started, who were demand partners which participated in the auction, how did they respond, which one of them bid and which one of them ignored the auction. Who won the auction? Was the ad shown to the user? Did the user view the ad? And did the user click an ad? All of this is aggregated in one row of my data set. So what we have to do, first of all, we have to label the session. we are doing supervised machine learning, and we need to tell to our machine learning model, hey, if you encounter this kind of session, a session which is similar to this one, you should react either positively, you should either start a session, or you should block a session. I will later on tell you explicitly how have we done this. Next step is the feature engineering. So now you must have a question in your mind, what is this feature engineering at all? So some models operate entirely numerically. Models do not understand what United States is. They do not understand what iPhone 7 is. In the feature engineering, you do two things. First of all, you select your features which you think are relevant for the prediction, and also you transform them in a format which a model can comprehend. And usually, models expect a collection of decimal numbers. So this is what we are going to do in the feature engineering. In the next step, we are doing the traditional split in machine learning. This is well-known machine learning theory. We split our data set on the training, validation, and testing data set. We're going to use training and validation data set to build the model, and we will test how well we are doing on the testing data set. The testing data set represents reality. It represents the production environment, and it represents the data which the model had not seen during its training. And since we are doing a binary classification, we are going to use a well-known metrics to see how well we are doing, such as precision, recall, and F1 score. So all of this is theory, but now we need to convert this into the practice. And in order to convert this into the practice, we need some tools. I did not mention, but 1 hour of our session data set is 500 gigabytes of data. So it's a half of terabyte of data. And in our production environment, when we build the model, we need to pull 24 hours of the data. So this is 12 terabytes of data. And there is simply no machine which can load all of this into the memory. And we need help from Spark. So Spark is a framework which gives us ability to keep on stacking processing power until we have enough resources. It's basically throwing money at the problem. From the machine learning part of the story, we decided to use TensorFlow. The TensorFlow is a feature-complete library. It is developed and maintained by Google. It will most likely be a long-term project, and we decided to go with this. Another reason why we decided to go with TensorFlow is because majority of machine learning engineers which apply at Smato have some experience with TensorFlow, and this makes the onboarding much easier. So all the tools are in place. Now it's time to scale everything up. And we need help from AWS. So in order to scale Spark jobs, we're going to use EMR. And in order to scale the TensorFlow jobs, we're going to use SageMaker. And both of those tools give me ability with a simple change of configuration file to change my infrastructure. Do I want to train on GPUs or CPU? Do I want to execute my Spark job on 10 machines, 20, 50, or 100? Simple configuration file does everything for me. Great. Everything is in place. Let's build machine learning models. And usually when you build supervised machine learning models, you follow a cookbook. You follow a recipe. So first you label your session, then you pick some of your features, combine some features, and then you do model selection. Maybe you want to train with neural networks. Maybe you want to train with decision trees. You pick your hyperparameters, and you train your model. And after the model had been trained, you take your testing data set, and you evaluate the model on the testing data set. And you look at the numbers. If you like the numbers, great, you're ready to go. But the reality is you will not like the numbers the first time, and then you need to go back to the feature engineering and model selection. And this is pretty iterative process, and this is unfortunately the reality of machine learning. And I'm looking forward to the future, because when I'm speaking with my older colleagues, which are now 50 or 60 or 70, and they tell me, hey, when I was your age, I was waiting for my compilation time for 30 minutes, for 1 hour. And this is the same scenario today, which we are in with machine learning. I need to wait 30 minutes for my model to train, or 1 hour, and let's see what will happen in the future when we get much faster hardware. Okay, so we started doing this. But pretty soon, we ran into some problems. And the problems were time-related. Time-related problems. So, biggest productivity killer for me is if I have to wait between two of my iterations. If I have to wait for 45 minutes between two of my iterations, my mind starts to wander. My focus is lost. I start thinking about other things. I go to the kitchen. I drink my 5th coffee of the day. I eat some sweets. I need to be engaged with my computer, and I need to have a fast feedback loop between me and my computer. So let me give you an example. One time, it was 1 p.m. I know my pipeline takes 45 minutes to be executed. I am at my desk. I schedule my pipeline, and I get up from my desk, go to the kitchen, play some ping pong, and it's 1:40. And I come back to my desk, look at the pipeline, look at my job, and I see EMR job failed. Execution time, 2 minutes. What happened? Unable to import library. And this happened so often, and we were starting to get frustrated. We realized that we cannot go on with this kind of workflow, and we needed to change something. So in 2019, we at Smato had a huge initiative to productionize machine learning models. And our CTO, Jerry Liu, wanted to approach machine learning as any other software development project. He noticed that there are many pieces of the code which can be reused across multiple projects. And he wanted for us to deliver him the machine learning framework. And also, while we were doing this development, we realized the whole environment is somewhat clunky. So basically, you're writing your Spark code in a text file or maybe in some notebook. Then you open your internet browser, you open a new tab, you go to the SageMaker, you open the notebook there, and then those things should be somehow connected. First of all, how do you version this? How do you write unit tests? It was really not cohesive environment. And we wanted to do end-to-end machine learning within integrated development environment. And we delivered the Smato ML framework. So Smato ML framework is a project which unifies everything what I described, the whole end-to-end machine learning pipeline. And this is never-ending project at Smato. Literally, every quarter on my roadmap, there's a huge box which says, improve Smato ML framework. And whenever we finish machine learning project at Smato, we take the learnings and we push it to Smato ML framework. And this is how we gain speed. So Smato ML framework is a project on GitHub. When we start a project at Smato, we start by cloning it, and we go on from there. And there are two main selling points of Smato ML framework. The first one is that it enables developer to focus on solving business problems for the company. And the business problems are solved in two files. The Spark file, spark.py, where you define how do you want to do the feature engineering and which features you want to pick. And in TensorFlow.py, where you say how do you want that your model looks like and what hyperparameters you want to use. Everything else is just plumbing and making things work together. The second selling point of Smato ML framework is how we gain speed. It gives you ability to execute your pipeline first locally on your local laptop, and you have a fast feedback loop. And after you realize that there are no runtime exceptions, no null pointer exceptions, you can scale everything up. And I have prepared a demo for you. You're going to see how do we execute machine learning problems, but it will come in 10 minutes. So when we were designing Smato ML framework, we realized that some developers prefer working within the notebooks. And when you start machine learning project, first thing you do, you explore your data. You look at your features, you see if there are any missing values, you are looking for correlation between the features and the target label, you are imputing some columns, and Jupyter notebooks are amazing tools for this. They are amazing tools for fast feedback between the machine and the developer. But there is a reason why we don't use Jupyter notebooks in our production environment. A couple of them. So first of all, they are slightly productivity killer. Because when I'm working within Jupyter Notebooks, I have to work within internet browser, and I don't have my shortcuts. The second reason, I cannot really debug my code. I cannot set a breakpoint, and more importantly, I cannot really step into the function of a third-party library. If I need to look up for implementation of third-party library, I need to open new tab, I need to Google documentation of this library, I need to check if my versions match, and then I can start reading. But the main reason why we don't use notebooks in production environment is the following. So on the left side, you can see I am reviewing the pull request of another developer. And on the left side, you can see the previous state of the file. On the right side, you can see the new state of the file. And it can happen that the developer changes one line of code, and the whole side-by-side difference looks like this. And there's a reason for this, because the Jupyter Notebooks are JSON files, and they contain a lot of metadata about the notebook. And this is error-prone, and I need to really focus when I'm reviewing this pull request, and usually we want to avoid errors, avoid mistakes, and we want to remove all the complexity if it's possible. And that is the reason why we keep all of our production code within the plain text files. So there are some talks at the conferences which I attend, and they're about machine learning, and they are great. And but when the talk is done, I stand up and I have some basic questions in my mind, like how did they do feature engineering, and how did they label their sessions? Which model did they use? And I don't want you to get up from this talk and have these questions in your mind. I want to break down to you how did we tackle this traffic filtering service. So let's start with the Spark. So in the Spark, I'm gonna explain to you how did we label the sessions and which feature did we use. So in order for me to explain to you the session labeling, I need to get back to this diagram. Let's imagine that we are in a scenario where edge request is coming to our core auction platform. And the core auction platform is propagating the request details to our demand partners. Now we can end up in multiple scenarios. And let's go with the first one, which never happens. I would be really happy if it happens that all demand partners bid, but unfortunately, this is not reality. We want to label this session positively because we want to tell our model, hey, if you encounter this kind of request details, you should start this auction. Another more realistic case is something like this. We send request details to our demand partners, 2 of them respond, 2 of them don't. We still want to label this session positively because we are holding an auction, and an auction has only one winner, and it's important for us to monetize the traffic for our publishers and also to provide an ad to our end users. And the negative case is the following. This happens in 90% of the cases. We want to label these kind of sessions negatively. So what I have to do, after I pull 24 hours of my session data set, I need to go across every single historical session, and I need to observe the actions of our demand partners and label them accordingly. And then I extend my data set with another column which says label. It's either 1 or 0. It's either positive label or negative. What about the feature engineering? Well, I need to tell you that while I was making these slides, this was the state of our feature engineering at the time. So we have this in production environment, but we keep on improving it as time goes on. And we keep on combining features, adding feature, but this was the state at the time. So for some features, we knew immediately what we want to do. For the time of the request, we knew we want to extract the day of the week and the hour of the day because this captures seasonality of our demand partners. But for some features, we had to separate them into the low cardinality and high cardinality. So now you have a question, most likely, what does this cardinality even mean? This is just a sophisticated word for how many unique values do you have. For instance, we operate on around 250 country code, and we consider this a low cardinality feature. For the connection type, we have 5 or 6 connection types. This is also a low cardinality. But for the ID of the publishers, we have tens of thousands, if not 100,000 of publishers, and this is a high cardinality feature. And we had to treat them differently. For the low cardinality features, we used one-hot encoding. And for the high cardinality, we used the feature hashing. I will break down all of these transformations. I'm pretty sure many of you are familiar with one-hot encoding, but let's see an example. First of all, let's simplify this situation. Let's say that we operate within 6 countries only. And let's say that we are one-hot encoding the country code. And within request details, United States appears. Every country gets an index. And what I have to do, I have to look up the index of United States, and I need to place the value 1 to the index of United States. And I will set everything else to 0. So this is one hot encoded country code, and I'm pretty sure many of you knew this. The feature hashing is less known transformation, and let me break it down for you. And once again, let's simplify situation. Let's say that we are feature hashing the publisher ID, the AdSpace ID, and the application ID together. First of all, these are independent processes. We take the ID, we compute some kind of hash, like MD5, and we get a resulting vector. And we do this for all the IDs. And the resulting vector is the one you can see at the bottom. This is simply a sum of those 3 vectors. And this vector has 2 really nice properties. The first one, the shape and the values within the vector are really similar to all of our other transformations. And this is important because our model is sensitive on scale, on the scale of the values within the vectors. The second good property is that model will always be able to make connections. This triplet is coming in trio, and this is really good for our prediction. So now when I explain to you how did we do our Spark job, how did we do the session labeling and the feature engineering, now it's time for me to speak about the machine learning part of the talk. So we decided to go for neural networks. We tried with both neural networks, we tried with both decision trees, we didn't see big performance difference. We decided to stick with neural networks for a couple of reasons. First of all, we know that neural networks are universal approximators. With enough capacity, it can learn any complex function. And the second reason is because we know the majority of gains in machine learning problems is within feature engineering. You can, if you don't prepare nice connections for your model between your features and your target label, you can use any model you want, you can give him any capacity you want, you will simply not get good results. So our neural network has 3 layers, input, hidden, and output layer. The input layer, we settled for 140 neurons. And it's important to note that the shape of input layer is determined by feature engineering step. If after you do the feature engineering, so you're representing one of your session with a collection of decimal numbers. If you end up with 140 decimal numbers, you need to put these 140 decimal numbers at the input layers of your neural network. The hidden layer was determined empirically. So we settled for 128 by 128 by 64 fully connected neurons, which yielded enough capacity to solve our problems. And there's a reason why we couldn't go with really, really deep neural network architectures, and I'm gonna explain it to you later on. Finally, the output layer is a one single neuron with a sigmoid activation function which maps the output to an interval between 0 and 1. And the semantics of this output is how confident the network is that there is gonna be anybody bidding within the auction. Where the value 0 represents, okay, there is nobody gonna bid, while the values more towards 1, the model starts being more and more confident. Hey, based on this incoming request details, I think somebody's gonna bid. You should start this auction. And finally, what I owe you is an explanation why we chose both Amazon EMR and SageMaker. Smato is AWS first company, and we want to use AWS tools to solve our business problems. And whenever we are in need of new tools, we check what Amazon had done for us, what AWS had done for us, and we try them out. And then we try third-party solutions, and we compare them. And this is exactly what we had done. And we didn't see much performance difference between the two, and we decided to stick with Amazon. And we have a big system engineering team, which has a lot of experience with security roles and whatnot, and it made integration within our environment much easier. Also, both EMR and SageMaker enabled us to create SMATO machine learning framework, and we decided to go with AWS ecosystem. But don't get me wrong, it was not easy. It was really difficult. It took us a month. We changed our strategy many, many times until we made it and make it work. So now it's time for me to show you SMATO ML framework in action. So I have prepared a demo for you, and we are going to do a couple of things. I'm going to show you our development workflow. And I'm currently located in my project file for the traffic filtering. And SMATO ML framework gives me ability to download a really small chunk of our session dataset, which we're going to use to execute pipeline locally. So first what we're doing, we're going to execute everything locally. We will realize that there are no exceptions, and then we will start scaling everything up. So let's start. I'm in my folder, and there is this folder raw datasets. And there is a Parquet file with a size of 200 megabytes. This is our session dataset. And what I'm going to do now, I'm going to open my development environment. And within my development environment, I have 3 files which are opened: the configuration file, the Spark file, and the TensorFlow file. And first of all, we're going to do local Spark development. We have to do a couple of things. We have to load the dataset from the disk. We have to do the session labeling, then the feature engineering, and after we are done, we're going to save the datasets back to disk. So I'm going to start a local Spark cluster. I'm going to execute this project. So as you can see in my console, the local Spark cluster is being booted up. The datasets are being read from the disk. And now we are starting with feature engineering. We're starting with the feature hashing and one-hot encoding. And you can see this executes pretty fast. And over here, I can set a breakpoint. I can write unit tests. And I can see that my code gets executed correctly. Now the datasets are transformed, and they are saved to local disk. And the format we're using is TF records. This is a format which TensorFlow can read. So I'm going to open my command line, and let's take a look. There is a new folder called Engineer Datasets, and you can see there's a split on the testing, training, and validation. And those part files are TF record files, which are result of our feature engineering. So I'm going to go back to my IDE, and now I'm going to go back to I'm going to open my TensorFlow file. And I don't really want you to read this file, but just so you know, there are a couple of things which need to be done. So once again, I'm reading the datasets back into the memory, the TF records. I'm constructing my model, and then I'm training my model. I'm using the training and validation test to train my model, and after the training had been done, we are going to evaluate our model on the testing dataset. So let's run this. I'm going to just say run me TensorFlow file and execute this project. And once again, we will ensure that everything is connected properly. Because when you're reading TF records from the disk, connecting the TensorFlow model with TF records can be pretty difficult. And this is, I don't know, if somebody writes this at first correctly, good job. I still cannot do it. I have to debug my code in order to do so. So now we can see the training had been done, and the results are pretty bad because we are training on a really small sample of the data. Now, when we have executed the whole pipeline locally, and this is pretty fast, we realized that there are no runtime exceptions. Now it's time for us to scale everything up. And from our empirical experience, if it executes locally successfully, it will be executed successfully in distributed environment. What I'm gonna do right now, I'm going to go to my configuration file. And I'm gonna tell to my Smato ML framework, your data sets are not located on local disk, they are located on S3 right now. And on S3, we hold our large data sets of couple of terabytes. Now it's time for me to execute the Spark job on EMR. And please note, I will not change one single line of code within my Spark file. Smato ML framework will first clean the previous directory on S3 of my previous job. It will package the whole project, and it will start an EMR cluster. So I'm gonna execute this. Now the project is being uploaded, and now the EMR cluster has been started. Within the Smato ML framework, I have a configuration file where I can say, hey, I want to execute my Spark job on 40 instances. Now, the EMR job is in the status of bootstrapping, is downloading all external dependencies which are necessary to execute the Spark job. And now he will do a Spark submit. This is basically, he will schedule a step to execute Spark job on this on this AWS infrastructure. And now the developer has a nice feedback loop. He can see your step is in state running. You need to wait until it finishes. And this usually takes around one and a half hour in our production environment. I have sped this video up, and I think I'm using a smaller data set, but after this is done, we are gonna take a look what are the results. So, the Spark job on EMR had been finished successfully. I'm gonna just go to my configuration file. I'm gonna copy the path on S3 where my files are, and I'm gonna do an ls. So list directory. And now what you can see, the format of the data sets are precisely the same as it was in our local execution. We have a nice split to training, testing, and validation. But those files are a couple of terabytes of data. And now finally, it's time for me to scale the TensorFlow job. So I'm gonna go back to my IDE, and I'm gonna go to TensorFlow, and I'm just gonna say, change me run configuration, run this on SageMaker. Once again, I didn't change one single line of code in my TensorFlow script. And now I started my SageMaker job. So what Smato ML framework does for me, it once again packages the project, it prepares the Docker images, it tells AWS, I need this kind of infrastructure. We are training on one instance, and there's a reason for this. We usually scale with GPUs first, and then we scale with multiple instances because the data transfer between GPUs is much faster than if you have to transfer the data between the network. So now the training has been started, and the developer, so this is a feedback from SageMaker. We can see how our training is progressing over time. We are monitoring our precision, recall, and F1 score. What I'm gonna do right now, I'm going to my method of building the model, and let's increase the capacity. Let's add more neurons. And maybe let's add another layer. And what I'm gonna do, I'm just gonna execute the project once more. And you can see I have two of my tabs opened. The previous SageMaker job and another one which is just booting up. The same story repeats. The project has been packaged. It will be placed on S3. The Docker image is gonna be prepared, and the training will start. And this is how we gain speed. Because you can train many SageMaker jobs in parallels. You can use different data sets. You can change the capacity of the model. And sometimes, over time, you even get intuition when you're just observing how your loss function changes. Are you doing a good job? And this feedback loop is important, at least for me. So this concludes the demo. And if I go back to my, I have opened my previous tab. this is the first job we executed, and I will not run it until the model converges. So let's do a slight recap of what we had done. We cloned Smato ML framework. We wrote our Spark code. We wrote our TensorFlow code. We executed everything locally. We wrote some unit tests. We ensured that there are no exceptions going on. And then we started scaling everything up. We executed the Spark job on EMR. We executed the TensorFlow job on SageMaker. And let's say we have a good model with a good performance. So what do we do now? We go to production. And now it's time for me to explain you how did we integrate the model in our production environment. It's time for me to explain you what is this traffic filtering service. The traffic filtering service, what it has to do, after the model building service builds the model, it needs to place the model on S3. From there, the traffic filtering service is going to load it into the memory and use it to answer the queries from our core auction platform. The traffic filtering service is a web application written in Java. It has no front end, it has only backend, and it has only one controller, only one endpoint. But it's not just one controller. It's more complex application than this. The controller expects the request details of an auction, and it returns back information, hey, you should either start an auction or stop an auction based on the prediction from machine learning model. I said it's not just one single endpoint, because if it was, we would deploy it behind SageMaker. We live in really dynamic environment. And we have business partners which are in constant communications with both publishers and demand partners. And sometimes it can happen that the publishers say, hey, Smato, what are you doing? You started blocking way too much auctions from us. Can you do something about this? And for me, first of all, to understand what is happening, to fix it, to retrain the model, and to deploy the model, it can take a day or two. And then it might be too late. So we wanted to have a red alert button which we can press and say, hey, traffic filtering service, if an ad request is coming from this publisher, simply whitelist him and ignore what model says until I fix it. What about the scale of our traffic filtering service? Now, this is something that we are really, really proud of. I'm going to show you two graphs. The top one represents incoming requests which are hitting our service every single second. The bottom graph is how fast we have to respond. On the x-axis of those two graphs, it is time. This is one Friday in September. And this is 24-hour period, which starts in the Friday morning and ends up the next day. And this is Central European time zone. On the top graph, there are 3 regions which are displayed, and the yellow one is United States. And in around 3 or 4 a.m., you can see that our service is being hit by 350,000 requests every single second. What does this mean? It means that there are 350,000 mobile phones which are requesting an ad from Smato every single second in the United States. And we have to respond really fast. Our traffic filtering service has to respond within 2 milliseconds. And this is the reason why we couldn't go for really deep neural network architectures. 24/7, around the clock, obviously, we don't serve all of this load of 350,000 requests every single second on a single machine. We have multiple machines hosted by AWS. And during the peak hour, we need around 30 to 50 machines to serve this load. But if you do some division, 24/7, around the clock, our service is hit by 10 to 15,000 requests every single second. And this means that our machine learning model is asked 10 to 15,000 times a second, what do you think, should I start an auction or should you stop an auction? And you have to respond within 2 milliseconds for every single request. So how do you do the integration? Well, usually today, when you're building machine learning models, today the language of choice is Python. The environment is rich, there's a lot of libraries, there's a lot of developers who have a lot of experience, the documentation is vast, and you usually really have to have a good reason why not to use Python. But the language which you're using in your service, where you serve your model, here is where things can get complicated. If your service where you do inference is written in Python, then you can consider yourself a lucky man. And why is this? You can say this doesn't make sense because, okay, there is a TensorFlow for Java. You can load your TensorFlow model in Java, and you can use it to serve model predictions. But this is not the problem. The problem is in the feature engineering step. Because let's remember, when an edit request comes to a traffic filtering service, I know the country code which is United States. I know the device model which is iPhone. But I cannot really give this to a model. I need to prepare a big decimal array which I prepared during the training. Because model does not understand what United States is. And why is this easy in Python? Because in Python, you can use the same piece of code which you use during your training in your inference service. You can do the same transformation during the training in your service. But in Java, I really cannot execute Python code. I mean, I can, but I don't have time. And also, I cannot run Spark cluster. Once again, I don't have time. Let me give you a slightly better explanation what the problem is. And once again, let's simplify the situation. Let's say that we are doing the prediction based on 3 features: the country code, device model, and the ID of the publisher. I'm gonna one-hot encode the country code and device model, and I'm gonna do the feature hashing for the ID of the publisher. And now I have 3 independent vectors. And this is all happening in traffic filtering service. And now I need to give array, one single array, to my machine learning model. Now my question is, which feature goes first? Do I put country code first or publisher ID? And how would traffic filtering service know this? Because traffic filtering service is not speaking with model building service. The model building service builds the model, and this is independent process. Another question is, what is the size of one hot encoded array? So we have to provide something to a machine learning model to do prediction. But now the question is, how would traffic filtering service know what? And this is the reason why we are exporting additional file during our Spark job. We call it the feature metadata. And the feature metadata contains some sanity check for developer, which time period did you use for the training, validation, and testing dataset, what is the size of your datasets, but there are 2 relevant information for a traffic filtering service within the feature metadata. The first one is the model input size. This says to our traffic filtering service, hey, when you're preparing your data for the model, the model expects an array of 140 decimal numbers. In the next step, we have a collection of transformations. And this collection of transformations say to traffic filtering service, hey, you should transform this feature in this kind of way. So let me give you an example. Feature hashing. Every transformation has a name, which features are transformed, and index start and index end. We are doing the feature hashing over here on AdSpace ID, Publisher ID, and Application ID. And after the traffic filtering service feature hashes those IDs together, when it's constructing a vector of size 140, please place this vector you just generated between index 0 and index 8. For the one-hot encoding, we are doing one-hot encoding on country code. There are mappings provided for you. If United States arrives, place value 1 to the index 0. And after you have constructed your vector, or your one-hot encoded vector, when you're generating your vector of size 140, please place it between index 8 and index 50. And you keep on going across the transformation until you get your vector of size 140 decimal numbers. After that, you provide it to machine learning model, and you ask him, what do you think? Hey, I just transform the request details into a format that you can comprehend. Can you tell me, should I start an auction or should I stop an auction? And this is how we replicated the Spark part, the feature engineering within our traffic filtering service. So what traffic filtering service has to do when it loads the machine learning model, it has to load the model into the memory, it has to parse the metadata, and it has to prepare it in such a format that it is fastest to execute. Okay, this was the integration of our machine learning model. It is now running in traffic filtering service. And now I would like to speak to you about the result of this project. And it is always difficult on a large scale, on an environment which is such a large scale, it's always difficult to predict will the benefits of the model outweigh the infrastructure costs which are required to run this. So when we replaced a rule-based model with machine learning model in production environment, we needed to use 30% more CPU on every single instance of traffic filtering service. And this transforms into $200 to $300 additionally per day. But the cost savings which were generated by replacing rule-based model with machine learning model by far outweighed the cost which is required to run it. So we started blocking 15% more sessions. And we are generating cost saving in 3 different areas. First of all, when the sessions are blocked, we don't have to pay for outgoing bid requests. And only if you sum up the cost saving generated by not having to block, not having to send outgoing bid requests, we already covered $200 to $300 per day. We are also doing cost savings in our core auction platform. It doesn't have to execute so many sessions. And finally, the data pipeline does not have to process so many events, and once again, cost savings are generated there. After we deployed machine learning model to production, we had to be careful because machine learning models are not perfect. They make mistakes. And we had to observe our revenue and see, did we get into a situation where we started blocking auctions which would otherwise yield revenue. But we did not see any significant negative impact on the revenue across the company. And finally, for the engineering improvements, I can say that truly at Smato, it's enjoyable to develop machine learning models. I am within my integrated development environment. I can debug my code, I can step into the function, and I can write unit tests. I can do proper source control, and I can do a proper versioning of my project. And most importantly, we keep on, as time goes on, we keep on improving SmartML framework, and we, as machine learning developers, we can focus on bringing value to the company, we can focus on solving business problems, and we improve our speed. So, thank you very much. This concludes my talk. I would like to get some questions from the audience. We have a couple of minutes left.